Good morning, my name is Krajewski, and I'm a second-year PhD student in Dr. Ziku Liu group at Pennsylvania State University. Today it is my pleasure to tell you about the data infrastructure I've been working on for the last year. To give you a brief outline of this talk, I would like to introduce 6 keywords. The first two are dealing with what sparked this work and how we were concerned about performance all along the way. The next two are dealing with how we implemented our infrastructure in a novel way. And then the last two are dealing with what are the intrinsic outcomes of our implementation. But before we begin, let me define 3 words so that we are on the same page as we go through this talk. The first one is material. In this case, we are going to mean a defined periodic discrete arrangement of atoms, essentially a postcard file with no partial occupancy. And this selection is made as opposed to just considering composition, so that we are not restricted to specific structures or patterns of structures like convex hull in the energetics of materials. And that selection allows us to have a much broader search space for our materials in the future, the benefits of which are going to be obvious later. Then we have property, and by that we are going to mean any defined property that we know exactly what it is. And then also it's not known a priori, so it's not obviously coming from the material definition. And finally, we have the descriptor. In this case, we are going to mean a set of properties or features that are defining the state of the material, and these properties are defined, known, and selected. This definition is more related to artificial intelligence definition of descriptor, rather than the one that you can see in a lot of talks at this conference, where descriptor is a single feature describing the material. That definition, I believe, comes from physical chemistry. And why I'm defining it as a set of properties or features is going to become obvious as we start talking about multiple descriptors describing the same material, and then being overlapping and having unique properties. Now, with the terminology established, let's look at a typical machine learning study. In this figure on the right, you can see a schematic of a tool that we designed last year. In general, you start with a set of structure files, your materials, that you then take into a descriptor generating code that creates this descriptor table, which is later used to make some predictions based on neural networks, trains on some big databases, and then you end up with a property data set that you desired. Such approach has some limitations, however. The first two, which are not as important, but still they are there, is that there is some reproduction cost and the reproduction learning curve. So if you deploy this tool, somebody needs to learn how to use it, and they need to spend resources to either train the models or get the models and run them. More importantly, however, if you look at this figure here, you can notice that the descriptor generation takes milliseconds per structure, while making the predictions takes microseconds. This introduces a very high cost of descriptor generation compared to making the predictions themselves. The reason is that usually descriptor generation uses some more expensive computations like Voronoi tessellation of the structure and then generation of a descriptor based on every atom attribute, or for example describing the material on a graph and then convolving on this graph to create a description of the whole structure. While making predictions is using some simple linear algebra in a neural network or random forest. Thus we can see there is a lot of room for improvement if we can omit the descriptor generation step from the modeling. We accomplish that by connecting our descriptor generating code to a MongoDB database on the cloud. Now, instead of calculating every descriptor directly, the code goes into the database to find out whether it was calculated before by somebody else. In the case of large datasets that were already calculated before by somebody else in the group, this is corresponded to speed up about 100 times, including all the overheads from the connection. What is very important for the rest of the talk is that the MongoDB database is a NoSQL database. What it means is that it's a non-relational type of database. Because of that, materials, properties, and descriptors can exist independent of each other. This allows us in turn to have a database that doesn't focus only on corresponding material to property. It can also look at mapping properties to descriptors or descriptors to properties. Now, with the core functionalities explained, we are going to expand the figure in the middle by adding new functionalities, and then we are going to build the infrastructure that we desire. We have started our expansion from a database into an infrastructure by moving the descriptor generation from the client side into the server side. Now we have a cloud of materials and cloud of descriptors, which are linked by these descriptor processors. On a basic functionality level, each of these descriptor processors accepts a PyMagen structure class and then returns a set of numbers that are corresponding to the analysis results. Each of these descriptor processors corresponds to a GitHub repository that is deployed on a server using the GitHub's submodule functionality. Every descriptor processor also corresponds to a publication that explains what exactly is done during the calculation. Now, once we have descriptor sets corresponding to materials in our database, we can move to doing some modeling, where we take these descriptor sets and we convert them into property sets that are interesting to us. To make this process smooth, like with descriptor generation, the machine learning models that we are using are standardized in the same way that they have the same basic functionality. They accept a numerical vector, and then they run a machine learning model and add the result to that set. The machine learning models themselves are stored on the great service of Zenodo provided by CERN, while GitHub provides repositories of codes that are handling the data processing into the model and out of the model. Now, once we obtain our property sets, we can link them back to the original materials that we used. This bidirectional linkage is provided by some sort of design agent that we define. On the most basic level, this is just material selection agent that can use either our website to find properties that are matching the desired ones. It can be queried to the MongoDB API that provides you very quick, very direct response, or it can be used of the curated software that we provide with a graphical user interface. In a more advanced form that we establish here is we can take these properties that we're interested in and we can design some inverse design agent that generates candidates that are likely to be what we want, then insert them back into the cycle, and then update the properties, and the cycle continues and rounds. To be fair, over the last slides, I provided you mostly with incremental improvements over the existing methods. So now, let's have a look over the next 5 minutes on the new things that our methods do while nobody else does it yet. Now, let me tell you about the first novel thing, which is auto-processing. It was directly inspired by my girlfriend. Whenever we come back home from doing groceries, I park my car in the garage and then I run upstairs to answer some emails. Then, 15 minutes later, when I come downstairs, a miracle has happened. The car is empty, the fridge is full, everything is well organized. So let's think what benefits we got here. First of all, we didn't have to unload the car. And then second of all, we didn't even need to know how to unload the car. So now the question is, can we do the same with materials? Here, by analogy, the MPDD database serves as a garage where we can park our materials. Then, once we park them, what happens is there's a series of events that gets triggered. First of all of these descriptor processors find out that there is a new material that they can process that was not processed before. This happens every minute and happens independently of the MongoDB database itself. They add these descriptors to all these descriptor sets that then trigger machine learning models to update property sets that are in this section of the database. This in turn updates all the information that is available on the website through the client or through the query, while at the same time updating the inverse design AIs that can change the candidate that they provide and then reinsert it to the database, and then again the circle is running. So now once we know what happens when we insert a material and how it automatically propagates through the database, we can start to wonder, can we do exactly the same thing with descriptor generating codes and machine learning models? And it turns out, yes, we can. On my earlier slides, I spent a lot of time emphasizing that these codes are designed to have exactly the same basic functionality, despite the fact that they are performing different operations and different analyses in the middle. Thanks to that, deploying a new descriptor generator or a machine learning model takes about 5 minutes, and then everything is done automatically. The node recognizes a new descriptor generator and then starts computing it automatically, like the rest. Exactly the same functionality applies to machine learning models. You only need to add a submodule based on the GitHub repository and then fetch a model from the node repository. Because of that, this infrastructure is perfectly suited for outside collaborators who know a lot about their specific material system and can extract information efficiently and then include their descriptors at very low cost into the infrastructure. Now, let me introduce to you the first novel what thing, that's the domain transfer. It solves small data problems that are present in machine learning and material science, where we have tens or hundreds or thousands data points rather than millions or billions like in the usual machine learning problem. It operates by looking at the property space and instead of going to the materials directly, going back through machine learning models, descriptor sets, descriptor processors, and to the materials. Going one level down from the property space into the descriptor space allows us to employ the fact that some of the properties are related with each other. And then we can design a model that is going to be run directly on the set that was already calculated, speeding up the process 10 to 10,000 times. Also, using a descriptor that's already calculated allows us to reduce the design of the model time because related properties often can share the descriptor. Furthermore, we can go all the way back into the material space, and since the whole database is linked into that descriptor, what happens is instead of having a few new materials that we design based on our model, we immediately get access to over 1 million materials that are already in the database. Such ability provides a unique opportunity for discovery of new materials, especially where they wouldn't be expected. Out of all things I'm showing you today, for me personally, the most exciting is the centralization of the computing that we perform here. As you remember, I told you that all the descriptor generators and machine learning models are modular. Because of that, we can easily detach them from the server, and that's exactly what we did. Now, all of these modules can be obtained from either GitHub or from GitHub plus Zenodo, and you can create your own node that connects to the database and then feeds back the data after computation. The first benefit of that is that everybody can start doing this. On my desk right now, there is a Raspberry Pi 4, which is currently calculating descriptors for local chemical environments at a rate of 40,000 an hour. Then it automatically feeds it back to the MongoDB database and extends our knowledge of materials. Thanks to the scalability, it can be run on any architecture. We have a server running on the Azure from Microsoft, as well as Penn State ACI servers. Finally, given enough resources, this makes this infrastructure capable of computing almost any amount of data, given that it's scalable and parallel. I know this slide is a bit messy, so let me reiterate the big picture. At the core of MPDD, we have a MongoDB database that links materials, descriptors, and properties together in a new fashion. It provides users with a variety of inputs and outputs. The computing side of the architecture is designed in a very robust way that allows multiple nodes to work in parallel and be created quickly based on GitHub and Zenodo repositories. From a simple user perspective, the only thing you need to do is input the structure, and then it's going to be automatically processed through the computing nodes into the descriptor, then into the properties, and then it's going to be available for view. To provide some concluding remarks, our self-extending infrastructure is currently live in its development version and is going to be open to public in May 2021. It contains over 1 million experimental or DFT relaxed structures, and each structure is linked to the database it came from or a contributor who uploaded it directly. If you're interested in contributing descriptor models, as I explained, it's a very easy process, and you can feel free to contact me and my advisor, Dr. Liu. Last Lastly, I would like to acknowledge all the people without whom this project would be possible: my advisor, Professor Zikui Liu, Professor Shunli Shang and Yuang from my group, as well as our collaborators from Math Department, Professor Jihao Shu and Dr. Jonathan Ziegel, as well as my funding agencies, NSF and Penn State's Institute for Computational and Data Sciences. Thank you.